In addition to looking at the biological processes and the things that can drive the potential upscaling of restoration there, the Australian government and the Reef Restoration Adaptation Program are also looking at very much out-of-the-box engineering solutions as well, things that we might not have even considered just a few years ago that we need to consider today. And so to talk us through one of those, marine cloud brightening, is Dr. Daniel Harrison with the University of Sydney.
G'day everyone. Actually, I'm going to talk through a few of the different ideas that we have in our app that basically cover physical engineering ideas and solar radiation management, which on a wide scale would be geoengineering. By definition, doing geoengineering is attempting to alter the climate of the entire planet. And so there's some geoengineering technologies here, but applied locally or regionally, they wouldn't technically fit the definition, but it's a bit of a grey area. Also, there's a bunch of people working in this program, as you've heard, and so a lot of the work I'm going to show in this talk is not my own, and it's done by some of these great collaborators down the bottom here. I'm sure everyone in this room remembers the moment that they fell in love with coral reefs. For me, I grew up in Sydney as the eldest of 10 children, which is a pretty unusual family size in Australia. And because there was 10 of us, we couldn't really go on holidays and fly anywhere. So we tended to go on holidays with these 3 4-wheel drives here. And it wasn't until I was about 20 that I first went to the Great Barrier Reef. We took these 3 trucks, my dad's big boat, a tinny that we bought by recycling aluminium cans, us 10 kids, and a big caravan way down the back there. And we travelled a few thousand kilometres up to the Great Barrier Reef where a very fortuitous event happened, as it turned out. The axle on my dad's boat broke, and since we're in the absolute middle of nowhere, it took 2 weeks to get a new axle. While we were stuck there, we were just a bit too far from the reef. It was 60 kilometres out, but we worked out that the boat used about 100 litres of petrol to get that far, and that was exactly the size of the tank, so if we took another 100 litres in jerry cans, we could get out to the reef. And so we did that every day. After a couple of days, my dad got tired of going. He said, "You kids, just take the boat, go have fun." So we spent 2 weeks going out in this boat, stopping for lunch, on coral cays or little islands, and just spearfishing and fishing and diving. And I was about 20 that time. That was, but I absolutely fell in love. It was the first time I'd ever been to a coral reef, and I've been back many times since. So it's not a small challenge that we're taking on in the Reef Restoration and Adaptation Program. We want to try and protect, to insulate an ecosystem that's the size of a country. The Great Barrier Reef Marine Park's about the same size as Italy, and we're trying to protect that from global changes. It's a huge challenge. The scale of the thing is just, probably beyond anything that's been attempted in terms of a marine ecosystem before. So what are some of these ideas that I'm going to talk about? First, we've got pumping. So this is probably the most commonly suggested technique to the Reef Restoration and Adaptation Program. Hey, why don't you go and get some cold water from deep and pump it up onto the reef, and problem solved. Mixing is a very similar idea, although rather than necessarily taking the water inside a pipe, there's various ideas of having big fans that hopefully draw up some water or just reduce the stagnation, right through to building undersea berms that would hopefully, the currents would hit them and then mix cooler water up. So it's the no stone unturned approach, as we've mentioned. So then we move on to some of the solar radiation management techniques. Surface films. So this is a molecular film that's just 1 molecule thick, housing a whole bunch of calcium carbonate, which are about 5 micron size. And you can actually see it in the top of the picture there, getting tested in a tank at Ames. And so this surface film, you could spread it out over the reef. It's completely biodegradable, and it reflects up to about 30% of the light from coming through. Shade cloths is a similar idea. It's been suggested to go and actually put shade cloths over high-value tourism-type reefs. And we'll move on to some of the more out there. So misting, what's misting? Basically, the idea of misting is that you can block some of the shortwave solar radiation coming in by creating a fog. So a fog is a bunch of particles or droplets in the atmosphere, And by reflecting the light, misting could either be done on a local scale, so just over an individual reef, or it could be done over a very, very large scale, in which case it's quite similar to the idea of cloud brightening. So cloud brightening, I know everybody's very interested in cloud brightening. So the idea of cloud brightening basically is that clouds over the ocean, every single cloud droplet needs to condense on a cloud condensation nuclei. Now over the ocean, most of these nuclei come from sea salt and from some sulfur-based compounds from DMS and the like. And so by adding more of this over the ocean compared to over the land, the numbers of these particles for clouds to condense on are much, much lower, where you typically over the land have thousands to tens of thousands of particles per centimetre cubed in the atmosphere. Over the ocean, the numbers are often in the tens to the hundreds. And so this means that clouds that are forming over the ocean, often there's the same amount of water vapour there, but each droplet is much larger because there's much fewer seeds for them to condense on. So the idea of cloud brightening is that if you added more of these sea salt seeds by just spraying seawater at a certain size into the atmosphere, allowing the water to evaporate, leaving the nano-sized salt crystal behind, that when the clouds form, they'll form with the same amount of moisture, the same cloud processes. It's not making clouds where there wasn't clouds before. But when they do form, that same amount of water vapor will be divided by many more smaller particles, many more smaller droplets in the cloud. And then this goes on to have two effects. The direct cloud brightening effect is that when you have the same amount of moisture but divided up by more small droplets, it actually reflects more of the sunlight back into space. It's greater scattering. And the second effect is that when you do this, you've changed the macrophysical properties of the cloud somewhat, and it's a little less likely to precipitate. Therefore, it may stick around longer, leading to more overall shading. And so, for the purposes of RRAP, you know, we've only been at this for about a year, and we have to evaluate a lot of different ideas right across the board. So, in the terms of these physical interventions, what we've mostly done is modelling, and we've tried to keep the modelling where we can to be quite generic. And so these ideas naturally group up into these three categories, which I'll go through each of now. The pumping and mixing, surface films and shade cloths, which provide just shading, and the misting on a large scale and cloud brightening, which can provide both shading and also some cooling of the ocean sea surface temperatures. So by now you're probably wondering, am I serious? Some of these ideas sound pretty out there, and look, they're uncomfortable ideas, and I think that goes right across this restoration space. You know, everything from the Mars spiders to coral propagation to these engineering ideas. You know, we don't want to be having to do any of these things, right? You know, for me, especially on the Great Barrier Reef, the area where I went as a child and first fell in love with the reef was one of the hardest hit in the bleaching of the last couple of years. You know, I would much prefer if things were still as they were then. So this is the NASA Land Ocean Temperature Index. And on the axis there, you've just got the global temperature, and across the bottom, the years. And what I've done is I've marked on the El Nino events in '98 and 2004 in orange there, where the Great Barrier Reef experienced a little bit of bleaching, but it wasn't too severe. You know, fast forward a couple of decades, and we had the very severe bleaching events of the last couple of years, which I've marked on there as red. And again, they occurred during an El Nino and coming off the back of a very strong El Nino. And you can see the El Ninos quite clearly there in the global temperature record as the little spikes occurring every 3 or 4 years or so. So the big problem that we're facing on the Great Barrier Reef is that in just 10 years' time, the global average temperature will be approximately equal to that which we experienced during 2016 and 2017 when we had these really severe bleaching events that killed up to 50% of the shallow water corals. I mean, they're very, very severe events. In just 10 years' time, that's going to be the average temperature. If we have an El Nino in that time, it's going to push it up an extra 0.2 of a degrees, a little bit less. What about 1.5 degrees? Now we're up into uncharted territory. An El Nino, when we're up there at 1.5 degrees average global temperature, we don't know what that's going to look like for the reef. 2 degrees is here. And as David mentioned earlier, you know, without massive global scale geoengineering, we're actually looking at just a few % chance now of meeting 2 degrees. And so we go further. So yes, I am serious. I think we need to consider these ideas. They may not be the ideas that we end up employing, but I think the no stone unturned approach is absolutely not just the right way to go. I think it's absolutely necessary. So we start getting into a little bit of the details here of the evaluations we've done over the last 12 months. We look first at pumping and mixing. So a very important parameter for moving cold water onto a reef, if you want to try and lower the temperatures that the corals are experiencing, is the residence time. So this is some modelling done by Mark Baird at the CSIRO using the eReefs model and downscaling to a whole bunch of individual reefs. There's about 19 reefs there. He's done a few more now. And what we see is that there's a very, very big difference. Sorry, so the plot, the heat colour there is the age in days of water on the reef. And what we see is there's a huge difference between reefs. Some reefs have quite good residence time. Other reefs, the water barely even doesn't stay on there for a day. You know, they're just basically where the water is flowing through. And we've also discovered, perhaps not too much of a surprise, that bigger reefs tend to have longer residence time, as do reefs that form their own lagoon. Okay, so we try and do some fairly generic modelling. You know, how much water would it take to make a difference? And for this, as with a lot of the modelling that we've done in RAP, we're not trying to predict the future. We're not trying to model, hey, this is what it's going to look like if we use this intervention. We're nowhere near that point yet. What we're actually doing is we're trying to bracket the problem. So this goes across all the modelling, including the cloud brightening. We're saying, okay, we have a pessimistic set of assumptions and an optimistic set of assumptions. What's the bracket there? And then if the bracket doesn't include a good outcome, then we're able to discard the ideas. So what you're actually looking at here is some modelling of pumping cold water onto Lizard Island. A lot of you might be familiar with Lizard Island because the Australian Museum has a research station there, which I'm sure many of you have visited. And it turned out that Lizard Island is probably in the top 1% or so of sites where you might want to pump cold water. This is because it has a long residence time in its enclosed lagoon, and it has very nearby a deep channel of about 40 metres deep where you can actually get water with a reasonable temperature difference to that at the surface. And so if you look at those bottom plots there, the residence time is longest at low tide. So this is looking at pumping in water at low tide, and you can see the spurt of temperature difference there with the blues being colder. And what we found is that even when we move up to an incredible amount of water, that's 4 sites there with 4 pumps per site, and each pipe bringing in 10 metres cubed per second of water. So that's you know, at each of those little sites, that's 40 metres cubed, 40 metric tonnes of water per second in, you know, you'd need pipes that were huge. And what we find is that you do get some local temperature cooling, but that it doesn't last very long, and even with this big effort, you don't really cool the whole lagoon. So basically, pumping up cold water doesn't look as a very viable restoration prevention technique, bleaching mitigation. So we move on to surface films and shade cloths. So what is a surface film? I explained it a little bit at the start. This has been developed by AIMS and the University of Melbourne and Deakin University. And essentially, you'd go out and you'd spread this film over the water that's biodegradable, and you might have to try and bund it in somehow. We're only just starting to look at the engineering options for how you might actually do this. But you are limited into how many reefs you could do this, because you've got to take quite a lot of material out there and you've got to keep redeploying it. Again, the residence time that I showed earlier is key. If you have reefs with water which has a long residence time, then obviously you're not going to have to keep replacing that surface film as often. And so again, Mark Baird's done some modelling here, and this is using his newly published bleaching submodel within eReefs. And what this model does is it actually tracks the build-up of reactive oxygen species as a function of temperature. It's actually completely mechanistically. So each photon coming into the corals is counted and then either used for growth, or if there's no carbon fixation available to grow, then the coral has to store that photon as reactive oxygen species. And then there's another algorithm in there that represents the rate at which corals are able to expel the reactive oxygen species. And so what we're showing here is basically the surface film can reflect up to about 30% of light. And so Mark's modelled here basically the base case during the bleaching event in 2016-2017 in the top panel, and in the bottom panel 70% of the light making it through. And so what we see is that if you can block off 30% of the light in this particular case, it's enough to greatly, greatly reduce the amount of reactive oxygen buildup. And so this plot's also colored so that the really dark reds are at the level that would cause bleaching, start to cause bleaching mortality. And so obviously you see a lot less in the lower plot. And so surface films and shade cloths could be thought of the same way, although we don't see shade cloths as being potentially that scalable, obviously. But surface films certainly show a fairly high potential as something in the toolbox that you could rush out and you could protect an individual reef, you know, a high-value larval source reef or a particularly important fishing reef or tourism reef. But it's not scalable to do at every reef across the whole Great Barrier Reef. And so then we move on to the larger scale ideas, misting and cloud brightening. I'll just go into a little bit more detail about what these are. So how would you actually do cloud brightening? So the idea is to actually get these nano-sized salt crystals that are naturally produced by the ocean. Normally these are produced and the amount of salt crystals goes up dramatically with the wind speed. So when you have a greater wind speed across the ocean, you have more small waves breaking, and some of those breaking waves are producing these nano-sized salt crystals that are essential for the cloud formation. So basically to do this in an engineering manner for the Great Barrier Reef, you'd need a whole bunch of stations, up to maybe 1,000 if you were to try and do the entire reef. And these stations, the technology is actually really quite simple. All they do is they take seawater, they filter out all the microorganisms and the plankton, and then they spray it at high pressure through a specially designed effervescent spray nozzle, which produces several billion droplets per second from a single little nozzle from just 0.4 milliliters of water. So that's how small these things are. You know, we're talking about actually nano-sized salt crystals. And in fact, one of the reasons that cloud brightening actually does have quite a lot of potential is that the leverage is enormous. So that nano-sized salt crystal, when it goes on to get activated into a cloud droplet, it grows 15 million times in size. It's very hard to get your head around just how small these things are. You know, again, 0.4 mils of water is a couple of billion of these droplets. Misting, on the other hand, you could do this in a bunch of different ways. You might also spray salt water, but you might vaporize oils instead, or use smoke generators. And so we can look at the modeling results here. This is looking at cloud brightening. This is just one of many, many scenarios. There's not enough time to go into it here, but there's a talk this afternoon that I'm going to give specifically on cloud brightening if people are interested in the details. But a couple of important things to note here is that the results suggest that we can get quite a big decrease in ocean sea surface temperatures. It's scale dependent, so if you do it over a larger scale, you get more temperature decrease. And also that you can see in the top graph there, which shows the solar radiation in the brightened and unbrightened case, the difference between doing cloud brightening and not doing it is those blue bits. And so you can see that you're very much just operating in the natural variability of clouds. So this is just a quick summary of the scale at which these operate over. So obviously we've got a range of scales with these ideas, from cloud brightening, which can do a very large area, down to shade cloths, which could obviously only do an individual kind of colony or collection of colonies. I'll skip through this one because I'm running out of time, but basically we made a conscious decision in our app. We've got 27 or so ideas, and we can't yet do quantitative risk assessment for all of them. But if we think a little bit about the risk here, then obviously with the scale of the implementation, the risk goes up. By doing risk management, we can take down the risk, both the likelihood and the impact. But an interesting thing, I think, is the reversibility. So cloud brightening, for example, the salt particles only stay in the atmosphere on average for 1 to 2 days. So if, for example, rainfall is getting affected in a way that you don't like, you can stop doing it and the effects are reversible. So just going through the intervention summary, pumping and mixing, it's very expensive, it has limited efficacy and very low scalability. Surface films seem like a useful thing to have in the toolbox for high-value reefs. Misting could potentially be done on a smaller or a larger scale. And cloud brightening, it shows the highest potential in terms of bleaching mitigation, but also obviously the highest risks. And then just finally, my general conclusions. None of these ideas can save the reef on their own. Action on climate change is absolutely essential. Social license to implement any of these ideas is obviously going to be key. they're very still uncertain. I don't know if these ideas are going to be the ones that we end up implementing one day. But also another finding from RRAP, I think, is that there's very, very few interventions that are truly scalable to the entire reef. That's my last slide. Thank you.